All right, so the one I want to start with, because it was kind of the trickiest part of our second exam here, was this competition between substitution and elimination reactions. And so remember, you were given this list of nucleophiles here, and you had to tell me for primary, secondary, or tertiary alkyl halides, whether they underwent SN1, SN2, or elimination type reactions. Right? And so we had this little chart here that we sort of filled in to make sure, because again, I gave you this part on the exam, but you had to know what each category went into here. So before we fill this in, let me just remind everybody what I mean by primary, secondary, tertiary. So again, we're going to fill in these boxes with these. Primary alkyl halides would be where that halide group is bound to a primary carbon. A secondary alkyl halide would be if that halogen is bound to a secondary carbon, and thus a tertiary alkyl halide would be if that halide is connected to a tertiary carbon. All right, so those are my three categories I have here on my Y part of my chart here. Right? And so for each one of them, we sort of could categorize whether, for example, a strong base, weak nucleophile would react with each one of these in an SN1, SN2, or elimination type reaction. Okay? So let's just kind of go through these together here. The two easiest categories here are the weak strongs. Okay? Because this category here, a strong base, but a weak nucleophile. What type of reactions, SN1, SN2, or elimination, do our bases promote? What is it? So bases are elimination. Okay, so if you have something that's a strong base, but a crappy nucleophile, it's going to be elimination reactions. So across the board here, these are all eliminations. And we did have like E1 and E2 mechanisms, but we said that for our purposes, they're the same thing. So we're just going to lump them together in elimination type reactions. But strong bases promotes elimination reactions. All right, and so what do I mean by an elimination reaction? Let's see one of those. Okay, so let's say that I have this secondary alkyl halide, and I'm going to react it with my bulky base, my strong base, weak nucleophile. What would be the elimination product of this reaction? What's the functional group of an elimination reaction? Yes, all right, good thing we're reviewing. Alkenes, double bonds is what you get for your elimination reactions. And in particular, you would get it on the more highly substituted carbon, right? So we'd have two choices. The carbon at the base of my halogen, it has to be involved in my double bond, right? But I could have one where it's on the end, or one where it's in the middle. And again, it's going to be the major product is going to be the more highly substituted alkene, right? So elimination equals alkene. All right. So going back to our chart here, again, this category I said it was easy to fill in because these are things that are strong bases, but they're weak nucleophiles. So they're going to be the type of reaction that bases like, which are, again, elimination reactions. So then the other category that's a little bit easier to fill in is the flip side, where you have a strong nucleophile, but a crappy base. Nucleophiles promote what kind of reaction? Not elimination, but substitution, right? And the tricky thing here is remembering that our primary and secondary substrates like to undergo SN2, whereas the tertiary undergo SN1. So all substitution reactions, the primary and secondary are SN2, and tertiary are SN1. All right, so let's see if we can remember the consequences of SN1 versus SN2. So we'll take one of our strong nucleophiles, weak bases, and we're going to compare this to what happens compared to a tertiary, which undergoes SN1. So take a second and see if you can't remember the substitution products of these reactions here. So substitution, right? So I guess in all of these, the S stands for substitution, meaning I'm going to be swapping functional groups. So in both of these reactions, I'm just exchanging that bromine for that sulfur. Right? That's what a substitution reaction is. You're swapping your functional groups here. Importantly, for the SN2 reactions, these had this stereochem inversion, which means that my wedge is going to become a dash or vice versa. So when I draw my substitution product here, again, I'm going to swap out my functional group, but I'm going to make sure to put my new functional group on a dashed bond instead of a wedged bond. So if SN2 has this inversion of stereochemistry, what's SN1 doing for us? Does both, exactly, right? So for this, you have to draw both stereoisomers. Do you want your exam? Is it Karen? All right, so I'm going to have to draw both the product where, basically where there's no inversion, so I'm just going to put that, swap out that new functional group and put it on a wedge, or on a dash rather. But then I'm also going to have to switch. And now this has to become a wedge, and this one, keep on mixing those up. One has to become a dash, and then the other one is the wedge. So you can see that I have these two products. In one, my new functional group is on a dash bond. In the other one, it's on the wedge bond. So that's the difference between our SN1 and SN2. That's why we had to distinguish between the two of them. SN2, there's this inversion. SN1, both. So again, that's kind of the two easy categories because one of them's strong, one of them's weak. The other one's the weak category here. For this one, the only thing that reacts with something that's both a weak nucleophile and a weak base are the tertiary substrates, and they actually both undergo SN1 and elimination type reactions. These ones do not react. Tertiary substrates are just more reactive if it's a weak nucleophile and a weak base. Primary and secondary just won't react with it at all. And then this one's another tricky one. Now these are things that are strong bases, but also strong nucleophiles. And so for this one, it has to do with this crowding effect, where the least crowded carbons, our primaries, are going to undergo substitution. But the secondary and tertiary, because these carbons are much more crowded and the nucleophile has a hard time getting to them, the base aspect of these substrates take over, and so we get elimination reactions. All right, so like the first thing you would do when you get your exam and you get this little constants page is to make this little chart, and that'll make it so much easier to go through and answer those particular problems, right? So that was the first thing we sort of practiced, was filling in this little chart right here. Again, you can kind of tell if you did it right, because you should have this little staircase sort of pattern here, where your eliminations are like this, like little Tetris pieces fitting together, versus your substitutions. Okay. Cool. All right, so that was definitely like the most tricky part of chapter, or unit 2 rather, and those types of problems that we did. So just to remind everybody that these sorts of things exist, these are going to be on our final, so make sure that you can do these types of reactions. All right, the other thing that we did in that exam, which was, generally speaking, people got down pretty well, but again, let's just remind everybody that this exists, are we have these rules for aromaticity. Right? And in particular, we should be able to classify compounds as aromatic, non-aromatic, or anti-aromatic. All right, and so just to remind us what those rules were, we had 2 rules. The first one was you had to be a fully conjugated ring, which means that you have to have this perfect spacing of your double bonds and single bonds such that it always goes double, then single, then double, then single, etc., etc. All right, so what we did when we looked at one of these molecules is we went through and we made sure that each carbon was associated with a double bond. So let me just give you an example here. We'll do 2. All right, so one of these is a fully conjugated ring, the other one is not. All right, and again, I can tell that this one is fully conjugated on the left because each one of these carbons is associated with one double bond. When I get to this other one, I got these 4 that are indeed conjugated, but then I have this one right here that is not associated with a double bond at all, so that breaks that ring's conjugation. Okay. And we said that if something violates rule 1, what did we call it? Non-aromatic. So this one right off the bat we can tell is non-aromatic. All right, and then we had our second rule, which is that you have to have an odd number of electron pairs. So if a molecule satisfies both of these rules, it will be aromatic. If it violates rule 1, it's non-aromatic, and if it violates rule 2, it's anti-aromatic. And then there were two special considerations here that we wanted to make note of. One, special consideration 1 was that carbocations do not mess up conjugation. So what I mean by that is if I took this exact same cyclopentadiene thing, but now this carbon up here had a positive charge, when I was going through and determining whether or not it violated rule 1, I would again count these 4 right off the bat because they're associated with double bonds. But that positively charged carbon, that carbocation, does not mess up my conjugation, so I count that as well. So this is indeed still a fully conjugated ring because that carbon up top has a positive charge. And the other special consideration was lone pairs get to choose. They get to choose whether or not they're going to participate in a ring's conjugation. And they're only going to do so when? If it makes it aromatic, right? If it doesn't, if it's going to make it anti-aromatic, they're just not going to participate. They're not going to play, right? They're going to stay out of the ring, making the ring non-aromatic. All right, so from this exam, let's focus on these two real quick. Determine whether or not they're aromatic, anti-aromatic, or non-aromatic. No, because so for example, if I had something like this, where this carbon has a positive charge, I would go around, okay, I'm going to include that, but I still have this one that messes up my conjugation. Right, so just because it has a carbocation in it doesn't mean that it's a fully conjugated ring. But I do count this one, right? I colored that one in blue because it still participates in that conjugation. But now it's this one messing everything up.
But it doesn't count as another.
It doesn't have electrons, I think is where you're going with that, yeah.
Does it count for the odd or even lone pairs?
It doesn't have electrons at all. So in this case, this has this one, well, it's non-aromatic, but it only has these 2 pair of electrons. I don't get to count anything with regard to the carbocation. The carbocation doesn't have electrons on it. All right. So when you get these fused rings, it's a little bit more difficult to see whether or not you're fully conjugated. But again, just go to each carbon individually and ask yourself, is it a carbocation or is it associated with a double bond, right? So even though, I guess these corners aren't too hard to tell, but these ones right here, it's a little bit tricky to see whether or not they break my ring's conjugation. But again, they are a part of a double bond. So I'm going to color that one and that one. This is also part of a double bond. So is that one, so is that one. So I have this fully conjugated ring. Okay, so I do not violate rule 1, but I got to go through and count my pairs. Oh my gosh. 1, 2, 3, 4. I have an even number of electron pairs, so this would be anti-aromatic. right? And clearly I wasn't too creative because this one also, go through, all these carbons are indeed conjugated, and again, I get to my carbocation, I'm going to count that one as well. Doesn't mess up my conjugation. And so in this particular one, I have 1, 2, 3, 4. So this is also anti. All right, so then quickly let's do one with the lone pair in it. See what's up with this. So again, I'm going to go through, determine whether or not my ring is conjugated. So again, this one right here might be a little tricky to see, but it is indeed associated with that double bond, so I'm going to count it. So I get all the way around, and then my question is my nitrogen with the lone pair, right? Whether or not that's going to participate in the ring at all. And again, it's only going to do so if it makes that ring aromatic, meaning it gives it an odd number of electron pairs. So currently it has 1, 2, 3, 4. So if that pair of electrons participates, that indeed makes it 5. And so that's why this will participate in this ring, making this an aromatic compound. Cool, so crash course on Unit 2 stuff. Okay. Yeah, I guess real quick. One more set of reactions that we had were of benzene rings here. All right, so take a second and see if you can't predict the products of, let's just pick a few of these here. No, I guess we should do 2 of them. Let's do these 2. Doing your exam. What's your name?
What day is the final one?
Wednesday.
Same time at 8.
No, it's at 8:45. It's a 2-hour exam, or that's your exam period. so let me just remind everybody, I know I'm going kind of quick, but I'm trying to cover as much ground as possible here. This particular chapter was all about what are called electrophilic aromatic substitution reactions. Importantly, you take a benzene, and you're going to swap out one of the hydrogens on that benzene ring, and we learned 6 of these reactions, right? So you want to know what each of these 6 reactions do. So with the Br2, that puts a bromine on there. The chlorine gas puts a Cl on there. Does anybody know remember what the nitric acid puts on there? NO2. This SO3H, this fuming sulfuric acid. And then these other 2 have a special name, Friedel-Crafts reactions. They stick an R group on there or called an acyl group, basically a carbonyl carbon. All right, so the first thing we did is learn these 6 reactions, right? But then if that wasn't hard enough, what we started to do was mix and match them, right? Because if you combine 2 of these reactions together, depending on the order that you do it, you will get a different product. You may get a different product. Because we said that some of these groups are ortho-para directors, and remember what my ortho-para sites would be. Well, so I guess let's just fill in this first one here because we got that. That would be, again, I suppose 3H. All right, so now when we look at this one, this benzene ring already has something on it, all right? So this particular group, the thing that's already on the ring, is going to direct the incoming substituent to either the ortho or para site. Those are ortho, para, or to the meta site on that ring, right? So whatever's already on the ring is going to direct whatever's incoming to a particular location. Okay? And we had this like big ugly cheat sheet list, but let me remind you real quick, the easiest way to tell is that ortho para directors have a lone pair next to the ring, right next to the ring. Directly attached to the ring is something that has a lone pair on it. All right, so for example, if it was an OH group, oxygen's got a lone pair. If it was a nitrogen, nitrogen's got a lone pair. Or if it was a halogen, halogens have lone pairs. All of these would be ortho-para directors, right? They have this lone pair located right next door to the ring. There's one exception to this that we want to make note of, and those are what are called alkyl groups, basically carbons, right? Carbons that aren't anything special. So the exception, which are also ortho-para, are alkyl groups. So for example, a methyl group, or an ethyl group, etc., etc. Some amount of carbons and hydrogens, right? Those don't have lone pairs, but they're still ortho-para directors. So those are the easier ones to spot. I mean, again, we have like this cheat sheet, but in terms of being able to just look at it and tell without having to memorize all these different functional groups, we're going to look for that lone pair or to see if it's just a plain old alkyl group. If it's not, then we can throw it in that metadirecting category. So for this one here, is this carboxylic acid group going to be an ortho-para or a metadirector? It's going to be a metadirector, right? There's no lone pair on this carbon here, and it's not just carbons and hydrogens. It's got that carbonyl group going on. So this is indeed going to be a metadirector. So it's going to direct my incoming substituent to that particular site. All right, and for these Friedel crafts, it's the carbon at the base of the halogen that's getting added to my ring. All right, so we learned these 6 reactions, and then we learned that if we mixed them and matched them, we could get different products, right? So if I do this reaction before this reaction, I'm going to get a different product than if I were to swap those. What's up?
So real quick again, when doing like say the third problem, you said like depending on which order we go into, which one do we do first?
So for this case, you have 2 things on the ring. So this is no longer orders. You're looking at what's already on the ring to determine, right? So it's like these 2 reactions have already been done beforehand. So you're not going to like switch the order for that. What we're going to have to do is go through and determine where both of these substituents direct to. So does this bromine have any lone pairs on it?
Yes.
Yes, right? Bromine has 3 lone pairs, so that's going to be an ortho para. There's already something in that para spot, so it's going to direct to one of those 2. And what about my nitro group? Is that an ortho para or metadirector? Metadirector. So that's also going to direct to what's meta to the nitro group, which are those same 2 positions. So if it's already got 2 things on the ring, they're always going to be in agreement. If this was the 2-semester course, there might be some logic as to if there was a disagreement, but we didn't ever cover any of that, right? So they're always going to, if there's 2 things on the ring, they're going to direct to the same positions. And that's the case here, right? This nitro group is a metadirector, and this position is meta to that nitro group. This is ortho para, and this position here is, in this case, ortho to that particular group. Right? So they're in agreement about where that incoming substituent should go. And that's always going to be the case. There's never going to be a disagreement. Okay? All right, so crash course in Unit 2 material. Let's go to Unit 1 here. First of all, hopefully the beginning portion is all sorts of straightforward in terms of how many bonds a particular element likes, right? Carbon likes to have how many bonds? 4. Oxygen likes to have how many bonds? 2. Nitrogen likes to have how many bonds? Right? And so if they break that pattern, then they have some sort of formal charge associated with them. All right? Drawing bond line structures was a big part of this beginning thing, but I've made you draw bond line structures to death at this point, so I think that we're all pretty good at that. All right? Importantly, let's do this one here, these rings, right? So we had these diagrams, these chair flip diagrams here, and we had to be able to fill them in to determine whether or not, or rather to determine whether these substituents are in the axial or equatorial position. That was the goal here. All right, so this is all about cyclohexane and the conformations of cyclohexane here. Actually, before I go into this, let me just talk about your final exam in general and like the format and all that stuff. For the sake of convenience in grading it quickly and getting it back to you quickly, it's going to be a multiple choice final exam. All right? And then we're also going to administer it through Canvas. So you're going to be filling in Canvas A, B, C, D, E, all that good stuff. Because what that's going to do is grade it immediately and put it in your gradebook immediately so that everybody knows what they stand as soon as they finish that final exam, right? You get your scores back immediately. What that means is you guys need to bring a laptop or some sort of other device in which you can take a Canvas quiz with you to class, all right? The library will lend you out a laptop if that's something that's problematic. If you don't have something like that, reach out to me and I can sort of help you get that all figured out, all right? But it's going to be administered in class, but through Canvas so that it immediately populates your gradebook and you get your score when you're done, all right? And then again, for the sake of convenience, so there's not any sort of drawing, it's going to be multiple choice sort of stuff. Obviously, the problems are going to be the same, but you won't physically have to, because that stuff takes for freaking ever to grade, right? So I'm going to be buried in grading as it is. And so yes, to the extent that we can streamline it in the final week, that's awesome, all right? So does that sound good? Everybody understand, right? So it's still in class. It'll be through Canvas, it'll be multiple choice, you'll be entering the Canvas, A, B, C, D, all that good stuff.
So we just need to recognize the right answer.
You will not be handing in any drawings to me. That's not going to say that I'm not going to try to be tricky and be like, hey, here's this thing and this thing. You got to actually know what you're talking about. But yes, it will be multiple choice. All right. So for this one here, all right, we had to be able to like take this picture and use it to fill in our chair flip diagram here. We had these bonds in pink that are pointed up that we called the axial positions. And then we had these bonds in blue that are pointed out, which we called the equatorial positions. All right, and our goal is to determine in the most stable conformation whether this is in the axial or equatorial and whether this is in the axial equatorial. All right, so let's work on just filling these in first. Kind of a point of confusion where people are like, where do I start numbering? It actually doesn't really matter. I mean, I tend to just go kind of clockwise, starting with 1 here, but if you made this 2 and then this 3, it would, it would be the same thing. You would arrive at the same conclusion. All right, so don't get too fixated on the numbering. All right, so I'm going to go to carbon 1. And this bond, this wedged bond, or I'm sorry, this dashed bond, is it pointed out at me or is it pointed into the page? What's the dash? All right, dash means it's into the page. The wedge means it's pointing out at you. All right, so looking at this cyclohexane here with these substituents, if I'm focusing on carbon 1, this methyl group is pointed down into the page. So I'm going to go to my 2 bonds here. This one's pointed up, the axial position. The equatorial position on this particular carbon is pointed down. So I'm going to put my methyl group on that carbon there. All right. Now I'm going to go over to carbon 4. Is this group pointed into the page or out at me? Into the page, so it's pointed down as well. So in this case, the equatorial bond is on top, and the axial bond is on the bottom. So I'm going to put this on my axial bond. All right, so we said it's not as simple as wedges are always axial and dashes are always equatorial. You got to look at that particular carbon and ask which bond's on top and which bond's on bottom. Right? If we take just carbons 1 and 2, for example, on carbon 1, axial is up, but on carbon 2, equatorial is up. So you got to look at that particular carbon and ask which bond is on top there. All right, so then we got to follow this when we do our little chair flip. Okay, so I put this on carbon 1 on the bottom one, so I'm going to go to carbon 1 and again put that on there. All right, this is after this chair flip has occurred. I'm going to go to carbon 4. It's on the bottom there, so I go to carbon 4. That position there. All right, so I got a lot of markings. Let me clear this up so we can see what's up. So which one of these conformations is more stable? The one on the left or the one on the right? Why the one on the right? Exactly. The big groups want to be in the equatorial position, right? That's the most stable conformation. So this one's the most stable. So I'm going to say that this is in the equatorial position and this is in the axial position in my most stable configuration here. All right, we got 5 minutes here, so let me just sort of remind everybody real quick. We had these radical halogenation reactions. These are the ones, actually the only reactions of alkanes. So these were covered in that like very second chapter, the first reactions that we covered. These require this reactivity series. Primary carbons versus secondary carbons versus tertiary carbons. I don't remember the numbers off the top of my head. Something like that. Where you had to determine where this chlorine was going to go based on how many there were and what degree of substitution there was. All right, so anyways, we did this one. I know there's examples worked out on Canvas. Let me just real quick remind everybody about the last portion of Unit 5, because that tended to be the trickier one, which were all these reactions of alkenes. So Chapter 3 was all about alkenes, and that was when we really got our first big batch of reactions, right? There was like 6 reactions of alkenes that we had to learn about. We only knew one of them up until that point. Then we got to Chapter 3, and we learned 6 different reactions of our alkenes. HBr, bromine and water, bromine all by itself, hydrogen gas, and then we had this mercury and this boron reagent here. So these 6 reactions were the reactions of alkenes. These are all what are called addition reactions. All right, so for example, for this one here, an addition reaction means that we're going to break, so let me just redraw my alkene carbons. These 2 carbons here, those are what my double bond used to be between. And in an addition reaction, both of those are going to have 2 new single bonds. I'm adding something to either side of my alkene. So with HBr, there was a hydrogen added on one side and a bromine added on the other side. All right. What about Br2? What are we going to add? What is it? 2 bromines, right? So you want to be able to look at your reagent and be able to tell what's going on here. You would add 2 bromines. All right. I'll talk about why I'm dashing and wedging here in a second. What about the H2? What are we adding? 2 H's. All right, and then these 2 reactions here, I told you when you spy mercury or boron, these are both adding alcohol groups, OH groups. All right, so just real quick, we got no amount of time. All right, and so the difference here, and this illustrates something that we had to know about each of these reactions, is for the mercury, the OH group is added to that more highly substituted carbon, where for the boron, it was added to the less highly substituted carbon. We had this special name for reactions that add to the more highly substituted carbon. What was that? Some Russian dude? Markovnikov, right? And so that was true for a lot of these reactions. We had to know whether it was Markovnikov. So for example, this one up here, I kind of didn't even explicitly say it, but that was another one. All right, so we had these 6 reactions. First of all, you got to know what they put on there because they're addition reactions. There are 2 more things that we had to know of each of these reactions, whether they were Markovnikov or anti-Markovnikov. And then the other thing is illustrated here, which is with these dashes and wedges, whether it was an anti-addition, where they were added to opposite sides, or a syn addition, where those 2 things were added to the same side. All right, so those were the things that we had to know. What's put on there? Is it Markovnikov or anti-Markovnikov, and is it syn and anti? That's what we learned about those 6 reactions from the alkenes chapter. So we covered a lot this semester, probably stuff that we maybe haven't thought about in a few months or whatever, right? So get to reviewing. It's going to be a comprehensive final. Again, it's going to be multiple choice and given through Canvas. All right, and you guys don't have classes for the rest of this week, right?